Uh, I will talk about big data query landscape in this talk. In this talk, I will survey a spectrum of query languages and query processing systems for the purpose of either online query processing, operational query processing, or offline analytical query processing. And I will compare their query capabilities as well. So here's a little introduction of myself. I'm a software engineer at Couchbase. I'm also a graduating PhD student from UC Irvine. And during my PhD, I have been working on AsterixDB, which is a big data management system developed at UC Irvine. And it is a research project. Right now, it is under Apache incubation. While in Couchbase, I have been working on a formal reduction from NoSQL query language to SQL++, which is 100% SQL backward compatible, backward compatible extension for handling rich data model. And here is the agenda. I will first introduce the area, and then I will briefly survey a bunch of query processing systems in operational systems such as Couchbase, NoSQL, Cassandra, and MongoDB. And then I will briefly talk about analytical query processing systems such as Hive, Impala, Spark SQL, and Drill. And after that, I will give a brief comparison on their query capabilities. And I will also briefly mention the research trend in academia, which is trying to unify those two kinds of systems within a single query interface. Finally, I will summarize this talk. So let's go to the introduction first. So in today's enterprise, people has a whole lot of online query processing requirements from either social network applications or B2B applications or B2C applications or mobile applications. And today, more and more enterprise companies using NoSQL databases to host this kind of applications. Traditionally, they were using relational databases, but due to the great scalability as well as schema flexibility offered by NoSQL databases, more and more enterprise, not only internet companies, but also established industry leaders start to using NoSQL to power their online applications. And those online reads and writes are hosted by NoSQL databases like Couchbase, Cassandra, or MongoDB. And usually, there is a ETL process happening, which happens usually at nights or at weekends where the workloads are not that high, to pull data from online storage to offline storage, such as Hadoop cluster. And after that, data scientists, business managers in an enterprise can leverage those offline data by running SQL queries, which are usually analytical queries over those data to generate business reports or to do decision-making analyses. These are the usual process happening at enterprise today. And those SQL on Hadoop systems, such as Hive, Cloudera's, Impala, Spark SQL, and Drill, they can do data analytics over Hadoop data. And alternative to the ETL approach, enterprises today can also using connectors to pull data from the online storage, and those data can be analyzed at SQL on Hadoop systems. In our previous sessions, people are talking about Spark connectors, Metanautics connectors. They are all using a connector approach. Either connector approach or the ETL approach has pros and cons. Connector approach has less data movements and data duplications, but ETL approach can better separate the online operational workload and offline analytical workloads. Currently in academia, there are two research projects aiming at unify online query processing and offline processing. SQL++ is a new language specification developed at UCSD. This is an extension of standard SQL to support rich data model. And AsterixDB is a research project developed at UC Irvine to support big data management and big data analytics. So in my talk, I will cover all these systems and compare their query capabilities. So in terms of unification, for the language unification, UCSD has developed the SQL++ language, which is 100% backward compatible with standard SQL, but it allows people to query JSON data. SQL++ allows you to handle or query rich data model like JSON. And it also exposes a bunch of configurable parameters for you to specify a language semantics. And for the system unification front, at UC Irvine, we have been building a big data management system, which offers a single query interface for both online query processing and offline query processing. It can, AsterixDB is aiming at scale out for both workloads. And it doesn't mean it uses a one-size-fit-all approach, but it takes smarter resource scheduling underneath to scale out both kinds of workloads. Okay, so I will cover several operational query processing systems here. So this is a simple program which does put and get, use the Couchbase Java SDK. As you can see, you can easily put data and pull data out from Couchbase server. This is great. This scales very well. This is very easy to program. However, what if you want to do more complex tasks? What if you want to handle some JSON data as your value, and you want to filter based on some JSON attributes, and you want to flatten some nested collections inside the JSON document? And what if you want to do group bys over some fields in a JSON document? What if you want to do aggregations? And what if you want to relate two buckets to do more powerful queries? If we want to do all this by Java SDK, it's doable, but it's boring and it's time-consuming. So that's why we at Couchbase invented NiCO. It's SQL for NoSQL. So NiCO brings the expressive power and elegance of SQL into JSON documents. So it extends standard SQL to allow you to query nested data, heterogeneous data, and internally, NiCO uses dynamic typing so that it gets more flexibility. It supports standard select pipeline, as Jared talked about in his slides. It can do joins, subqueries, set operators such as union, except, intersect, just as standard SQL. It can also you can also use onNest and onNest to process nested recursive data. So I will give you an example here. We have two build sample documents. As we can see, they are nested because in the first build sample document, it's a ABV field itself is a JSON document. It's heterogeneous. As we can see, the type field and the category fields does not exist in the second build sample document. But we can run the standard SQL here. We can still select from the build sample bucket. We can filter based on the type field. And we can project category, type, and a nested field in ABV. So it will give you the intended result as a JSON document. So as we can say, this is elegant, this is powerful, and this is backward compatible with the SQL convention. Now I will give a brief introduction of the Cassandra query language. It is called CQL, Cassandra query language. It's a SQL-like query language, but it's in a much restrictive form than NiCO. As we can see, Cassandra supports lookups, filtering, and ordering, but it doesn't support aggregation, join, subqueries, unnest. Not only that, more importantly, it requires a schema declared upfront, while NoSQL is schema-free. So as we can see, in SQL, it doesn't have schema flexibility. So here are two example queries expressed in Cassandra. They are both doing filtering. As we can see in the second query, you have to say allow filtering because country is not indexed. If you want to query, if you want to filter any fields which is not indexed, you have to say allow filtering. Well, in NoSQL, you don't need to say that because NoSQL allows better logical physical separation. Here is the MongoDB query language. MongoDB offers a JavaScript-like query language. It's more powerful than Cassandra. It allows lookup, filtering, ordering, aggregation, and unnest, and it's schema-free, the same as NoSQL, but it doesn't support join. It doesn't support subqueries. As we can see, you can get a sense what MongoDB query looks like by check these two queries. As we can see, MongoDB queries basically tweak the data format together with the query semantics here. The same queries, second query does a group by on the date, basically month, day, and year, and it gives the total price, which is the sum of all the prices, and the average quantity, and also the count. It's just a simple aggregation query. As we can see here, in MongoDB, it's more verbose than NoSQL. This is MongoDB, so okay. So I just covered the online query processing part. Now I will dive into the analytical query processing systems such as Hive, Impala, Spark SQL, and Drill, and to see what they look like. So let's first get into Hive. How many people are familiar with Hive? Okay, there are quite some people are familiar with Hive. Hive basically is a SQL query language over Hadoop. It supports more data types than standard SQL. It supports bags, which is array. It also supports map, and it also supports nested records. So the data types are more richer than SQL. A Hive query can be compiled to a bunch of Hadoop jobs or a single test job to run in shared nothing clusters. To give you an example, here is a simple Hive query. Imagine you have two Hive tables. One is for your Facebook data, one is status updates, and the other is profiles. Now, this query joins the status updates with profiles based on the user ID to basically get the profile status updates for each user, and to filter based on a particular date, and then group by school and do a count to give you statistics to say how many Facebook status update from each school. And the result will be inserted to yet another Hive table called school summary. This is a Hive query. This is a SQL. And this query can be compiled to two MapReduce jobs. The first MapReduce job does the join, as we can see here. M1 is the mapper job. It scans two table, filters on the status update table, and the reduce sync basically prepare the data for shuffling. And after shuffling, join happens to do the inner join here. And then after join, the pre-aggregation for the group by is done. And then the result are dumped to HDFS. And then the next MapReduce job is kicked off to do the intermediate aggregation in M2 and to do the final aggregation in R2. So as we can see, this query can be compiled to two MapReduce jobs, and each the boundary of boxes are tamping on file systems, either on local file systems or HDFS. The tamping basically offers fault tolerance properties to allow the query scale to very large data set on very large clusters. Okay. Impala is developed by Cloudera. It supports standard SQL 92. It can use either HDFS or HBase as a persistent storage. Instead of using Hadoop MapReduce as the runtime, it has a native massive parallel query processing engine. So for the same Hive query, if you run this in Impala, since they support almost more or less the same query language, so if you run this in Impala, Impala will compile it into a DAG of query plan here. First, we do scan filtering, and then we have a hash join, and after hash join, we do a pre-aggregation. And after pre-aggregation, we do a merge aggregation. After the final merge aggregation, the results are dumped to HDFS. So as we can see, instead of 4 boxes in the previous slide, we only have 1 box here, which means the evaluation is pipelined, and there's no tamping in the query processing pipeline. It offers much better performance with the compromise of fault tolerance properties. This is how Impala look like. And Spark, as we know, Spark gets more and more popular. In previous sessions, we have talked about Couchbase Spark connectors. And Spark, people has also built SQL on top of Spark, which is called Spark SQL. Spark SQL supports both SQL query language as an interface, as well as data frames as an interface. Different from SQL, data frames is more procedure-oriented instead of declarative. So as here, the same query in SQL is just doing a global count based on some filtering conditions. The same query can be written in data frames by, first pull the user data into the variable users, and then does a filtering over the users, assign this to young, and then finally count how many elements in young. They basically express the same thing. And the architecture of Spark SQL is that both SQL queries and data frame queries are compiled to the same substrate, which is unresolved logical query plan. And then by checking the catalog, those unresolved logical query plan can be typed, which is a logical query plan. And this logical query plan will be further compiled to a set of physical plans. And by checking and comparing the cost model of each physical plan, one physical plan will be eventually selected. And this physical plan will be further compiled to RDDs, which are Spark jobs, to evaluate this query. This is Spark SQL. And the next system is Drill. Similar to Impala, Drill supports standard SQL, but it also supports nested data. And in addition, it doesn't require a schema declared upfront. It can do schema inference. Drill can read data from either those traditional databases like Oracle, MySQL, Teradata, where there's a centralized schema, and the whole the whole table is statically typed, and the schema could be managed by DBAs. It can also read data from HDFS, where the data is self-described, like JSON files, or it doesn't have a schema, but Drill infers such a schema. For example, CSV files, Drill can infer a schema of that. So let's Drill. Okay. So now let's go to the interesting part, which is comparison of a spectrum of all these languages, and how some academic researchers are trying to unify those query processing capabilities. Okay. So in this part, I will first briefly introduce AsterixDB, which is a big data management system we have been building for 5 years at UC Irvine, and right now it's under Apache incubation. It's a system unification effort. And then I will talk what is the ideal query language should look like for processing semi-structured data like JSON documents. And after that, I will give a comparison of the spectrum of all these languages. Then I will introduce SQL++, which is a language unification effort developed at UCSD. And finally, I will show how NoSQL can be reduced to SQL++. Yeah. Okay. Let's first briefly look what's AsterixDB. AsterixDB is a big data management system. It supports NoSQL data model with schema flexibility, which means you can have a schema up front or not have a schema up front. And AsterixDB allows you to seek a trade-off between relational databases, where everything is static typed, and NoSQL store, where there's no type at all. So it can allow you to declare a partial schema. It has a declarative, full-fledged query language called NQL. It has partitioned native RSM-based storage. It has secondary indexes, such as B tree, R tree, and keyword indexes. It supports single-row transactions. It also has spatial temporal data types. Now, in order to support external data sources, it supports HDFS data accessing, and it also allows you to indexing the data you already have on HDFS. Similar to Impala and Drill, it has a native MPP query execution engine. So the storage part allows to support operational queries such as lookups, updates, data ingestions, and the external data accessing, and the MPP query execution engine allow analytical query processing. So let's AsterixDB. Okay. So since you have listened to a whole bunch of sessions talking about JSON documents, NoSQL, how we handle query JSON documents in Couchbase, so I will briefly, to walk through what an ideal query language should look like. So as we can see, nowadays, instead of using flattened relational data, more and more enterprises start to using JSON-based data model. In JSON-based data model, the data model support nested tuples. For example, we can have recursive data structures, and the nesting level can be arbitrarily deep. And we want to schema flexibility. For example, when your business evolves, you want to change the schema. For example, adding certain fields into the schema, but you don't want to run a slow alter table query in standard SQL. And also, there are more and more heterogeneous data in enterprises as we use JSON document. For example, every document could look very different. And also, the query engine, query language should should well support complex values like record, collections, and so on. So let's still look at the school summary query we have talked about previously about the Hive query. So this is the same query. And now what if I have those new requirements? The first requirement would be, here I have a count to aggregate like how many status updates are posted from each school. But instead of count, what if you want to select the latest 3 status update from each school? Instead of the count aggregation function, you really want to run is a subquery here. Sorry. Sorry, where's my mouse? Okay, so, sorry. Anyway, so what if school is, what if school is not in the schema of the profiles table. So if you want to run this in Hive, school has to be part of the schema of profiles. What if school is missing in some profiles, but present in some other profiles? What if school is a nested tuple? For example, I have some attributes for the school. So you see, all these cases will break in SQL. But ideal query language for semi-structured query language should support all this. OK, now let's go to the exciting part where we compare all the query languages and query processing systems we talked about. First, we compare the data model of those query languages. As we know, in SQL, the top level values can only be a bag of tuples, which means in all the variables in a SQL query language has to be bound to a bag of tuples. As we can see here, all the systems have this requirement, but AsterixDB doesn't have this requirement. A variable can bind to an arbitrary type of value. And whether those languages support heterogeneity, which means, for example, in NoSQL, we can handle JSON documents, and JSON documents are by its nature heterogeneous. So NoSQL will support heterogeneous data, but as you can see, all those analytical SQL compatible systems like Hive, Impala, Spark SQL, Drill, they cannot support heterogeneous data. And Cassandra cannot support heterogeneous data as well. Cassandra neither support heterogeneous data. MongoDB support heterogeneous data, and AsterixDB also support that. For collections like arrays, bags, and maps, each system has different supports. Here, P means a partial support. For example, in Hive, a map can only store scalar values, while in Cassandra, arrays and maps can only store scalar values. Not only that, they also have a size limit of that. And for nested tuples, as we can see, some of the analytical systems support that. NoSQL support that, but Cassandra doesn't support that. Okay. Now we compare the types of those query languages. So as similar to program language, a query language can be static typed or dynamic typed. NoSQL is a dynamic type language, which means at compile time, there's no type information. All the type information are carried in tuples and will be checked at runtime. So this is what NoSQL and MongoDB does. But all the analytical SQL on Hadoop systems, they have to enforce static type checks. The difference of dynamic type checks and static type checks is that dynamic type checks allow you to have more flexibility in terms of schema. You don't need a schema declared up front. And you can, every tuple can be of a different type. But static type systems doesn't allow this kind of flexibility. As we can see, AsterixDB support both dynamic type systems check and static type check. All the rest of attributes are used only for static typed systems. But as we can see, none of the SQL on Hadoop systems, neither Cassandra can support other features like any type, open type, union type, and optional fields. But AsterixDB can support all of them. Any type basically is that at compile time, if you have no way to decide what a value's type is, in AsterixDB, we tag it as any type. And in runtime, this concrete type can be found and checked. Open type is more specifically about partial schema, where you know part of the type of your tuple, but some of the rest fields can be self-described and can be checked at runtime. Okay, these are about types. Now let's talk about path navigation. Path navigation means when you want to navigate a tuple or array or map. Tuple navigation means you use dot to access some fields inside a tuple. Array navigation means you use an integer index to access an array. And map navigation means you use a map key to access values from the map. What if the path navigation has the following cases? In relational or traditional databases, absence in path navigation will be arrowed out because, for example, in SQL, if you say select name from a table, but name is not present in the table, SQL will report error for those. And if you want to, array navigation absence means if you have an out-of-bound array access, what will happen? Map navigation absence means if the key is not in the map, what will happen? In addition to absence, there could be cases of type mismatch. For example, when you access field from a tuple, but you accidentally access values field where the value, some variables field, but the variable itself is not a tuple. SQL cannot allow that. And for array access, for array access type mismatch is that you access by index for some variable, but the variable itself is not array. What will happen? For map, it's similar. As we can see, all the SQL on Hadoop systems, they mostly error out those cases. For Cassandra, they error out all these cases. For MongoDB, they don't support array and map. But as we can see here, the nice thing is NiCO never fails for those cases. It never reports errors because NiCO has this missing type. For these cases, NiCO, the evaluation result of these cases will be missing in NiCO. So that's a nice thing of NiCO. Okay. Now let's compare the select clause in all these query languages. As we can see, the first column is whether this query language allow you to project a tuple where a field is a subquery. And this subquery doesn't return a scalar value. As we can see, only NiCO and AsterixDB allow that because those non-scalar subqueries will be a collection in the result document. But Cassandra cannot, and MongoDB cannot do that because they don't support subqueries. And SQL cannot do that because SQL, nested and collections are not naturally built in SQL. And the second criteria is whether those query languages allow you to project tuples with nested collections. As we can see, some SQL on Hadoop systems allow that. Impala doesn't allow that because Impala doesn't have any collection data types. It only supports standard SQL 92 data types. Cassandra cannot do that because Cassandra doesn't have subquery capabilities. The last criteria is whether query language allow you to project a non-tuple in your result. As we can see here, NiCO allows you to do that. For example, you can say select element or select row or select value in NiCO. It will allow you to project non-tuples in your result. You will get a collection where the element of the collection is not tuples. Cassandra cannot do that. MongoDB can do that, and AsterixDB can do that. Okay. The last comparison is the from clause of all these languages. The first criteria is subquery. As we can see, those SQL on Hadoop systems support subquery because subquery is a built-in element in standard SQL. But Cassandra's MongoDB does not support subqueries. And for joins, those SQL on Hadoop systems support joins because that's what they are good at for large joins. This is analytical queries. For NiCO, it supports joins, For Cassandra and MongoDB, they don't support joins. For AsterixDB, it supports joins. The third and fourth criteria is the inner on-nest and outer on-nest. Inner on-nest means, in NoSQL, for example, we have the on-nest statement. It allows you to flatten nested collections inside the tuple out, and the result for one tuple, it will generate as many tuples as the size of the collection inside this record. Outer on-nest has a slightly different semantics. For inner on-nest, which means if the collection inside the record is empty, this document will be killed in the result. But outer on-nest, similar to outer join, it allows the original tuple present in the result, no matter the nested collection is present or not. A last criteria is ordinal positions. It's not a so important feature. It basically allows you to keep track of the positions of the values you scan from a collection. Okay, so now we briefly talk about what is SQL++. Especially interesting is the plus part. SQL++ is a language extension to standard SQL. It is 100% backward compatible with standard SQL, but it allows you to query JSON-based data model. It supports inner and outer flattened clauses. Note here, it's the inner and outer flattened clauses allows you to do more powerful nested processing on the nested collections. It can support arbitrary subqueries in select. And the nice thing is all these features are supported by NoSQL now. And in addition to those language elements for processing semi-structured data, SQL++ also expose a set of configurable parameters for semantics. For example, it exposes parameters for you to specify the behavior of past navigation failures, equality evaluations, and collection cohesions. We have worked hard in NoSQL to make everything consistent in terms of those semantics. Here we give the SQL++ configuration parameters for NoSQL. For past navigation, as we can see, for all those traditional past navigation failures in standard SQL, NoSQL will evaluate them as missing. For equality comparisons, NoSQL support complex types. For example, you can do group by on a nested record. You can do group by on a collection type. The group by key type could be those types. And the other part are basically saying what's the behavior of equality comparison when now is part of the left-hand side or right-hand side, or missing is left-hand side and right-hand side. And last few are about when you end now and true or false, when you end missing true or false. Those are the semantics of those corner cases in NoSQL. They are corner cases, but they are important for you to understand language better. Okay. Now we go to the summary. In my talk, I put NoSQL in a bigger context of those big data query processing languages. As we can see, for operational query processing, NoSQL is the trend, but SQL is back now, but with extensions. We have to extend SQL to processing nested data, to handle heterogeneous data. That is what we are working hard to make those happen in NoSQL. And for the analytical query processing systems, as we can see, not many systems can support rich data model. But it is a must. And we believe the trend will be to have a unified language interface to provide the capability for either operational query processing using the NoSQL data model or analytical query processing, still using the NoSQL data model. Okay, thank you. Questions and answers? Any questions? Okay.
The question is about the missing part.
Mm-hmm.
For the flexible schema, is it a necessity or it's a requirement? So I believe sometimes I feel like without missing, the flexible schema in Couchbase might not work with Nickel. It's kind of a missing part which you put it in using the missing keyword.
Yes. Missing is not a keyword. It's a type. It's a type of value. So it's a special type. So allow the query processor to understand the data and to process those data gracefully and give you the intended result instead of error out the query. Okay. More questions? Okay.
The traditional relational databases spend a lot of effort in query optimization.
Yes.
So with these new SQL extension for NoSQL, do you see that the same kind of challenge will be there for query optimization for these new SQL?
For this new SQL, yes, there are challenges because previously people spent decades to build a query optimizer for relational data. And now we have language specifications, we have clean semantics, and we are working hard to get optimizations for those query languages. So it takes time, but eventually it will get there. And those new SQL is a must for people to process data in this new data model.
Thanks.
Okay, more questions? Right. Mm-hmm. All right.
Yingyi. All right, that was fantastic. Thank you so much, Yingyi.